we will continue in this lecture on the fundamentals of relevance and fundamentals of artificial intelligence machine learning in the context of additive manufacturing. So, what are the examples of AI ML application? So, this AI ML is expected to revolutionize our lives in general and also frontiers of the technologies in particular. So, if you see this automatic translation, that also is given by the AI ML, traffic prediction, web search and recommendation engines, online fraud detection, medical diagnostics, very useful, text and speech recognition, image recognition, right. So, these are like in all the different examples of the real world, this particularly what machine learning is expected to revolutionize. So, this one I have explained to you in the last lecture and I am explaining again, because these are the key definitions or key aspects that you should remember. What is artificial intelligence? That science that uses algorithms and techniques leveraging computer to mimic human intelligence. Second one is machine learning, like algorithms whose performance improves over time as they are exposed to more data. That means that machine learning predictions for any M processes where you have, let us say 100 data sets are there, certain specific algorithms may work better with 100 data sets. But if you go to 1000 data sets, you will find that another algorithm perform much better in terms of the performance metrics. What is the performance metrics? I will come back to that in next few slides. So, therefore, the performance dynamically changes as you have more data sets in your environment or in your within your accessibility domain, right, or whether more and more data sets you are utilizing in this machine for the machine learning predictions. Supervised learning trained on labeled data, unsupervised learning it is without labeled unlabeled data, and then third one is the reinforcement learning to take the action to change the state so that you can receive rewards. Now, what is deep learning? Deep learning is a subset of machine learning where multi-layer neural networks learn from a vast amount of data. So, deep learning is a subset of machine learning. Often many students or some of the researchers often use these terms in an interchangeable manner, that is not correct. So, deep learning is a subset of machine learning and machine learning is again in one of the subset of large artificial intelligence, that is a large umbrella. The most important thing that I have explained in the last lecture, but I am just leaving the key message here for you to remember that AI ML is most relevant in the absence of any established relationship between dependent and independent variables. I have explained this in reference to 4D bioprinting, which represents one of the most recent advances in the field of additive manufacturing. Right. What are the key terms? What is data set? Data set is a collection of data that is used during training and testing. What is training? What is testing? I am going to explain to you soon. Hypothesis space, that is set up all possible hypotheses. Inductive learning is that inducing a general function from training examples. Evaluation, that use some metrics which help analyze performance of the models. Training, that are data set split used to train the model and making the system able to learn. What is training? Training is the fraction of data sets which are used to train the model. So, you take certain algorithm based on you are trying to develop this model and then you want the data sets to train the model, so that this system will be able to learn how to use this model and what is the efficacy of this model. Testing is the data set split used for evaluating the best model performance. As I mentioned in the fundamental definition of machine learning, the performance performance becomes better and better over time when they are exposed to more number of data sets. So, that means if the training and testing data sets also increases, so or particular testing increases, the model performance also becomes better and better. K-fold cross validation, that is a resampling method that uses different portions of the training data sets and validate a model on different iterations. Hyperparameter tuning, that is essentially choosing a set for optimum hyperparameters for a learning algorithm. So, training data sets and test data sets, typically scientists have used different proportion of the training and test data sets, and for various number of examples they have found that 80-20 ratio, 80% of training data set, 20% of test data sets. I repeat, 80-20 ratio of training to test data sets provides optimal performance for the best model when they use the different algorithms, ML algorithms. So, that is one message that you get. Second one, what are the inputs and outputs that I have mentioned? So, inputs can be either experimental data or modeling data or computation data or both. Experimental data can be process structure property correlationship, computation data can be generated by DFT, MD or FEA. Output, what is the output? It can be a continuous value like regression analysis can be property, the output can be printability, output can be defect. So, one of the major things that I am going to show you with examples from our own research, that how machine learning models can be used for the defect predictions in the AM processed metallic structures, because the lower the volume of the defects, better will be the property of the AM parts, right. And then this property also depends on the nature of the defects, right. That I am going to explain to you in the subsequent slides, where you will see that how 3D printing, how 3D printed parts or 3D printing related experimental results, and they can be better assessed by classification algorithms using that ML model. What is the historical perspective? 1764 is the birth of Bayes theorem is published, that is a probability theory, okay, probability based theory. And this probability based theory kind of is the essentially the source of this today's artificial, or the origin of today's artificial intelligence. Then comes Ada Lovelace, that is lays the foundation of the first algorithm. Then comes George Boole, on his name that Boolean logic is being created, and Boolean logic is known in today's world. Then comes Alan Turing. So, this Alan Turing proposes a machine that can learn. Arthur Samuel, that creates the first computer program, that is IBM computer. Modeling, that first artificial neural network is created. Then Rosenberg and Sejnowski, that is the NetTalk, that is the framework. Geoffrey Hinton invents the term deep learning somewhere around 2006 onwards. Google creates an unsupervised neural network 2012, more than 12 years ago. AlphaGo beats the first human player, and then AlphaFold 1 technology that is predicting protein structure is created 2018. So, you can see that that over last several hundred years, 1764 and today's 2024, right. So, over this so many years that it starts from Bayes theorem, that is very fundamental theorem. From there, today's machine learning is essentially developed, and then it is going to revolutionize human life in general. What are the basic steps of machine learning? That is some of the data like observations, measurements of training data sets. If you remember, train to test data sets is 80-20. Right. So, you have to infer some pattern or relationship within the data, that is the learning phase, and then make predictions regarding the previously unseen data. So, consider a data set of materials, for example, composition, manufacturing conditions, and then it has a property. And this property, depending on what is the material composition, this property can P1 to Pn, but this material composition in input, output is your property. Property you are most interested to know the property. But there are some unseen things that is called fingerprint. So, you generate the fingerprints while using this kind of algorithms and learn the relationship between composition, manufacturing density, and predict the density or property of new untested materials with arbitrary compositions or manufacturing. So, as I said that machine learning is a branch of artificial intelligence that is concerned with the design and development of algorithms that allow computers to evolve behavior based on empirical data. One of the things that you learned in the previous slides is that performance improves over time with more data. So, in the traditional programming, let us say C or C++ programming, So, what would happen that you give the data and you give the program, then you get an output, right. Then computer will run the code, that program, and then you get the output. In the machine learning, what you have learnt already, the training is 80% data, you split the data sets into training and testing. You with the training data, you allow the system to learn from these data sets. Then you generate learning methods, and then testing data is feed into this, then it is able to predict. So, you get the data, you get the output of this one learning method, then you essentially generate a program here using computer. So, without even programming, you can run this particularly develop this machine learning model, that is what has been also mentioned to you earlier. So, basic workflow in the machine learning model, this is like a generic description. So, you have a raw data. So, you in the raw data you have to see the dimensionality reduction or extraction features and output, then you have to split the raw data, training, test data. You can also keep some amount of data, percentage of data as validating sets. So, training data essentially train the model, and this particular model, there are different model like hyperparameter selection and validation. I will show you more examples of that. And test data, the 20% data, that is what has been mentioned, that is allows you to estimate this model. And then there is a new instances, and then final model and predicted output. So, first phase is your extraction phase, second phase is your training phase, third phase is your prediction phase. But the question is reliability of the prediction. How reliable is your predictions? You can predict many things, but whether these predictions is statistically reliable, what are the performance metrics that you consider which allows you to be also convinced about the machine learning based predictions, and what you have to believe and you have to trust the data, right. So, therefore, input data quality is very important, right. So, otherwise, as you know, in that conventional programming what we learnt in the undergraduate student, garbage in, garbage out. So, if your garbage is into the program, the output also will be the garbage, right. So, therefore, one has to be very clear about the quality of the input data, what data you are taking and whether you are randomly choosing without any bias, 80% the training data sets and 20% testing. The moment that you actually allow your personal bias to be involved in the data set creation, testing and training data sets, that actually bound to give you these unrealistic predictions or unreliable predictions, that is the better word, unreliable predictions. So, performance matrix over the time that you learned in this last lecture, this today's lecture, that performance of the machine learning becomes better and better over time as it is exposed to more and more amount of data. Then question is that how you can define performance matrix or how you can evaluate the performance of any machine learning model per se. So, one is that R square. Now, R square is a term that you have learnt in your basic course on statistics, correlation coefficient, or here you can also see coefficient of determination. Right, coefficient determination or sum of the squares of residuals divided by total sum of squares, and then if you have to deduct from one unity, so then you get R square. So, R square should be close to 1. So, that means it should be close to 0.95 to 0.99 or somewhere like that. That is the best performing model. Then second performance, so here you can see that this is that ideal line 45-degree line. If you use the, if you plot actual versus predicted. So, data is scattered right across this 45-degree line, and then if you get actual versus predicted, this data is scattered, and therefore, you can see that this how you can establish the statistically reliable performance parameters, performance matrix, and this one of them is R square. Second one is the root mean square error, RMSE. RMSE, it is 1 by n sigma I is equal to 1 to n yi minus yi average hat square, and that is 1 by n is this, you have to divide it by 1 by n. So, this particular formula it is called root mean square error. This value should be close to 0.0. Okay. So, if it is close to 0, R square is close to 1, that is the best performing model. The third one is that the residual error distribution. So, what you see here from actual to predicted, here I refer to this particular plot again. So, your actual data points is somewhere here and the predicted data points is there. So, this minus this will give you error for all these different data points, right. So, what is the residual error and what is the probability density of this residual error, and as long as this residual error distribution gives you a good Gaussian type of distribution, that is more like a uniform Gaussian type of distribution, that means that particular model will give you best predictable results. So, I repeat 3 parameters, one is R square, one is RMSE, third one is the residual error that has been just explained, that it should be Gaussian distribution. And here you can see 2 different type of columns are there which are being plotted, and these columns have different color, and one is for the testing data sets and one is for the training data sets. So, training is this one, the larger column, and testing is this one. Both for testing and training, it should give rise ideally to Gaussian distributions, and then you can consider that there is particular machine learning model that you have generated that will likely to give you the reliable predictions. So, this is that residuals calculated from for training and testing data sets, good residual plot, high density of points close to origin and symmetric about origin, and best performance as I mentioned close to 1, RMSE close to 0. And this is the residual error distribution, you see that it should be close to 0. So, that maximum density. So, if you take the probability density, this is the highest probability density, you can see close to 0, right, and this is the residual error distributions. Epsilon is the residual error, and x is that essentially measurement that that actually what I said, that actual versus predicted. This is the actual, this is the predicted. So, in the predicted distributions, in the predicted data, what is the residual error distribution? If the maximum is close to 0 origin and then symmetric about origin, or origin means 0 0 and this is also 0 0, then it is a best performing ML model. So, this is the criteria for the best performing ML model, right. Now, training and testing data set, generic rule is that training is the process of making the system able to learn. So, there is no free lunch rule that is applicable to training. Training set and testing set come from the same distribution based on specific assumptions or bias. I mentioned to you before that there should not be any human biases involved when you randomly distribute 80% training data set, 20% testing data set. The moment you apply your bias, you are bound to get unreliable predictions. Performance, there are several factors like types of training provided, background knowledge, type of feedback and learning algorithms used. Two important factors here, one is the modeling and one is optimization. So, suppose this is a universal data sets, right, this is the overall data sets, and you get the data acquisition, then you distribute it, training data sets, and testing data sets are essentially unobserved data sets, then you essentially distribute 20% of the testing data sets. Algorithms, I mentioned before that it can be supervised learning, that is prediction and classification. So, classification is essentially discrete levels and regression is the real values. So, there are two major things in the supervised learning classification algorithms. Example is that defect predictions in the AM parts, additive manufactured parts. Regression, classic example is that you vary the process parameters, you would be able to see that what is the weld pool depth, weld pool height, weld pool area and so on and so forth. Unsupervised learning, so this is the concept of supervised learning. Unsupervised learning, I am talking about this now. Unsupervised learning is the clustering. So, it is a small domain clustering, probability distribution estimation, dimension reduction and so on. Semi supervised learning or reinforcement learning is the decision making and also for class machine. Supervised learning overview, the supervised learning model mapping from one or more inputs to one or more outputs, and model is a family of equations. Computing the inputs from outputs, that you give inferences. Model also includes parameters, parameters affect output of the equations, right. And training a model is essentially finding a parameters that predict outputs well. This well word essentially is very important and it is not a qualitative term, it should be statistically reliable and also it is good predictability. Good means it is trustworthy predictability. Notation, X is actually a Roman letters input, Y is output, the model is equal to Y is equal to Fx. So, X is essentially function of square brackets, that is how it is to be learned. Normal is returns vector, bold is returns vector, capital bold is returns matrix. Okay. So, any times if you put capital X, that means it is a matrix. So, training data set from I pairs of input output variable. So, this has been shown here, let us say xi yi, then I is equal to 1. Loss functions or cost function measures, now bad model, that is also has been shown here, or on short, in short, for short it is L phi, that returns a scalar that is smaller when model maps inputs to outputs better. So, it decreases, this value decreases when the model performs better and better, that is the major message that I am going to tell you. regression. So, regression, this in traditional sense, regression essentially means model input connected to model output through a model and or real world output. So, this is the example, is a laser power, scan speed, layer thickness, hatch spacing, that is for example in the metal additive manufacturing, right. Let us say SLM. So, it gives you 4 values like different values, then it gives you 340 like a data sets, then you get the geometry, melt pool, density, porosity, roughness, mechanical properties, yield strength, ultimate tensile strength or percentage elongation to failure. So, there is a univariate regression model like one output real value and multivariate regression model, that is multiple outputs and real value. So, this is the question for regression analysis which I am going to show you with real experimental results, particularly with case of supervised learning models later on. Now, examples of the 1D linear regression model, for example, it is a simple linear model y is equal to phi naught plus phi 1 x. So, where is x is the input variable, phi is your and phi functions is phi naught phi 1. So, this is y offset and that is the slope of this one. Examples of the 1D linear regression testing, this is the output, this is the input x, y versus x, and then you see that there is a variation there. So, degree to which this is the same as training, that is called generalization, and often it should not lead to overfitting or underfitting. It should be just fitting the data with these particular model examples. K-fold cross validation, these are like more advanced topics in the machine learning. So, as I said that there should not be any bias, and particularly training data sets and testing data sets, that we need to take care of the overlapping of the test data sets. So, what is the first step? You split the data into k subsets of equal size, and this k fold cross validation means this is essentially k subsets of equal size of the data. Second step is that use each subsets in turn for testing the remainder of training. This means learning algorithm is applied to k different training sets. So, here for example, in the training sets, if you see, this is the MAC1. So, this is the mean of this particular training data sets. So, this is the training fold, this is the validation folds. So, you randomly put this MAC1 to MAC5 like that, that k different models. Then you essentially use the best model, and while selecting the best model, then you use the different ML models like KNN, K nearest neighbors, SVM support vector machine, ANN artificial neural network, DT decision tree, RF is the random forest model, GBM is a gradient boosting machine. And you learn later on there is something called tree based learning models, which is a more generic term. So, you put these best models, your training data sets you apply, you try to fit it, then you develop the capability to predict the sum of the test data set, that prediction goes to the final models. So, often the subsets are stratified before cross validation is performed to yield stratified k-fold cross validation, and then error estimates are averaged to yield an overall error estimate, because error estimation that I have mentioned to you with this error distribution, that distribution of the residual error, that is important, and residual error distribution should be Gaussian in nature with the maximum probability close to origin 0 0, and also this should be uniform, this should be like this should have a Gaussian type of distribution both for training data sets and testing data sets. One of the classic example is linear regression. Even when people did not know about this machine learning, artificial intelligence, linear regression has been used in statistics for quite long, for many decades or centuries I would say. So, linear regression, as the name suggests, y is equal to mx plus c, that is classic equation for describing a line. So, m is the slope, x is the y intercept, and y is equal to mx plus c. So, here what you can see here, it is y is equal to a naught is your line intercept, a1 is the slope linear and a1 is linear regression coefficient, and epsilon is your random error while predicting the target variable y, and x is your independent variable. So, mean squared error, essentially what you have seen here, this is the mean squared error MAC is essentially mean squared error when I have mentioned while describing this k-fold cross validation in the last slide. So, mean square error is nothing but 1 by n is sigma I is equal to 1 to n yi minus aixi plus a naught square, and that means that you put yi here, this minus a naught is this one. So, that is this is essentially the residual error square, that is mean square error, okay. And n is that size of your data sets, right. So, gradient descent, that is used to minimize the mean square error by calculating the gradient of the cost function. So, this is your cost function, and then use gradient descents to update linear coefficients by reducing cost function. This is some examples that slope is phi 1 and intercept is phi naught. So, how this loss function will evolve, that is L phi. You remember this L phi in some of the earlier things that I have mentioned, that L phi is the loss function and it decreases typically as the model performs better and better, okay. So, this is the performance metrics that I have already mentioned. Another things that has been mentioned here, for example, just I am giving you different example. Here loss capital L is the value of 0.19, here phi naught. So, what is phi naught and phi 1? Phi naught and phi 1 I think I have defined you before. Yeah. So, phi naught and phi 1 essentially are, you can consider as like a naught and a 1 here. So, yeah. So, these are like this is the essentially output data, this directly plotted in a board line, these are like scattered data points. So, this dotted line essentially indicates what is the deviation from the predicted with the real one. So, this is least squares loss function. So, L phi is a function of xi phi minus yi, that square, and this for the large number data sets I is equal to 1 to I, it is phi naught plus phi 1 xi minus yi square. So, essentially it gives rise to something called epsilon, that is residual error, right, that is square. So, 1D regression function, again it shows a different way of representing the same thing. Here along this is a 3D plot, L phi versus slope phi 1 versus intercept phi naught, that is also just to show or illustrate the example of 1D linear regression, 1D linear regression loss function. So, I stop here, I will continue in the next class again with some of the remaining concepts with examples of the artificial intelligence and machine learning. Thank you.